Hey friends, it's Ben again. This is my second go at recording this particular video, so pardon me if I seem a little bit exhausted by it. So the thing we're taking a look at here in the vector calculus class is that divergence theorem, which is the last section in the textbook. After this, we're going to be talking about things that are more differential equations related, because the original design for this course was to have things broken roughly in fourths and to have this stuff here at the end, the end quarter of the semester, be something about that. Different design has come forth because we need to do something with presentations, which means projects, which means extra time for y'all to work on things. But that means that you should probably start thinking about, is there something that I know of I can work through that's of interest to me? And we'll talk about that a little as we go along. So, all right, but this divergence theorem, let me go ahead and share screen with you here so that you see what's going on with it. And then I have to cross my fingers and hope that it will actually connect. Great. So here's your statement of the divergence theorem. You get a continuously differentiable vector field F, and you have some region W with its surface, with that little partial symbol before it meaning surface, surface W being outwardly oriented. So then the flux integral across the surface, and by the way, notice the little circle here. When you had a circle on your line integral, it meant a closed curve. Here it means a closed surface, okay? But your flux integral across this closed surface is going to be equal to the volume integral of the divergence of the vector field inside that volume. Now, I am not going to try to draw a picture and justify this to y'all. The essential notion of it is that divergence of a vector field sort of means it's pushing away from a given point. And so when you talk about divergence of the vector field, it's talking about a net pushing away. If you've got a pushing away over a volume, it has to be pushed away somewhere. And the way it's pushed, the place it's pushed away is through the surface. And that's why the flux integral, which is a flow through a surface, connects into this divergence, right? But we have to recall that the divergence is defined by taking the gradient operator and dotting it with the F vector. So your divergence will always result in a scalar, not a vector field. For 3 dimensions, it would just be take the X, Y, and Z derivatives of the X, Y, and Z components, respectively. If you were doing something in higher dimensions, then you have to have some way to express it. And your divergence then is going to be a summation of the partials of these functions with respect to the variables that have to do with their coordinates. So let's take a look at something here. This particular problem, I kept dropping minus signs and just little errors. So I've written it out ahead of time. Bear with me here. We have this surface. It's going to be a cylinder with top and bottom being z equals 0 and z equals 2. So if we think about this here, the surface is going to have a bottom and a top, and then these sides here. And when we talk about verifying the divergence theorem by direct calculation, that is asking you to go through and do both of the calculations and make sure that you get the same thing. When you do these on your classwork stuff, if my answer does not agree with yours, but your 2 answers agree with each other, figure that there was some arithmetic mistake somewhere. If your 2 answers don't agree with each other, then check to see whether one of them agrees with my answer If it does, hopefully that means that the error is in the other one and you can track it down. I literally just spent 20 minutes looking for something. It turned out that I wrote a 2 when I meant to write a 1, or a 4 when I meant to write a 2, or something like that. It's just ridiculous. So, all right. So we're going to come along here and do the top surface first. And since that top surface is circular, we parameterize it like so. I know that your textbook goes ahead and works out an example where they say something like x and y and 2 for this. And you can certainly do that, and that gets you your in vector, but it sure does not help you with the parameterizing here, okay? And so when y'all get that comment from me on some of your work, it's because I'm trying to look out for you in what's going to let you actually do the rest of the work on the problem. So, all right, so we can go ahead and take the G sub r and the G sub theta and take the cross product. We have done this before though. The normal vector is going to turn out to be pointing upward because it's the flat surface z equals 2. We could have also just gone that route with it. But you do have to realize that it's pointing out, not in. Therefore, it's 0, 0, 1, not 0, 0, negative 1. Okay? So then the 2x, we replace the x with the r cosine theta. The 3z, we replace the z with 2. And the 3y, we replace the y with r sine theta. We're dotting that with 0, 0, 1, which means the first 2 entries just drop out. So this means that what we have to integrate is the 3r sine theta dr d theta. Now, if you notice, we can factor it into r's and thetas. And if you factor it into the thetas and integrate 0 to 2 pi for sine theta, you get 0. Doesn't really matter what this one turned out to be. It would turn out to be, I guess, 3/2, but you're multiplying it by 0, so you get 0. Okay. Now we're going to do the bottom surface here, and it is basically the same work. We set it up, we do the cross product, but it's pointing out, so it has to go down, so we get a -1 instead of a +1. Doesn't make a difference in the answer at the end, but conceptually, you ought to catch that particular tidbit. So we set up our integral, and the only difference in the f is that the middle entry is a 0, but the in vector has that negative in it. When you dot, you'll get -3r sine theta. Do the same thing with separating it apart, and you get 0 out of it. Okay. Now we'll do kind of the body of the cylinder there, the sides of it. Remember that the r is equal to 1, so you're going to parameterize that with cosine theta sine theta, and then z. It could be anything you want to call it, but I call it z. Take your g sub theta and your g sub z and do your cross product and work it out. We've done this one before. Turns out to be cosine theta sine theta because we need to have that pointing outward. Okay. So then we come along here, and for the 2x, replace x with cosine theta. For the 3z, replace z with z. That wasn't much of a replacement, but you know. And for the 3y, replace the y with the sine theta. And we get to dot with this. The 0 there means that we drop this out. And so we end up with a 2 cosine squared theta and a 3z sine theta. Okay. Now we've dealt with this kind of thing before since we're integrating 0 to 2 pi. That part is going to turn out to have an integral of 0. This cosine squared, though, when you integrate cosine squared from 0 to 2 pi, you get pi. And we've had that come up enough that you all just know that. So that means that we've got 2 times the pi. This is that thing I was mentioning earlier that I copied the 2 down as a 4. Drove me nuts. But you integrate 2 pi d theta from 0 to 2, That just means multiply by 2, you get 4 pi. Okay, so that was a lot of calculation. And the more calculation you do, the more you get a chance to drop a negative. So, all right, let's see what happens when we apply the divergence theorem. The divergence of that 2x, 3z, 3y, derivative of 2x with respect to x is 2. The derivative of 3z with respect to y is 0. The derivative of 3y with respect to z is 0. We get 2 out of it. So our integral of the divergence is going to be just the integral of 2, but it's just a constant. So you have a constant 2 times the volume of the region. The region is a cylinder, so you calculate its volume with pi r squared h, and you get 4 pi. Those two answers agreed with each other, which did not happen the first time I worked through this. So it's very easy to just make copying errors, okay? So, but the big thing that you need to spot there is when you applied the divergence theorem, the main use of it was in suddenly being able to just do a calculation in your head because you turned it into a volume times a number. If you get more complicated vector fields, you're not able to pull that, but often you do, okay? All right, so this time around, we've got S being a surface, which is a cone, and it's going to be pointing downward, and of course, we're orienting this all outward, and the z equals 1 is the top of the cone, and then the bottom of the cone is going down like that. All right, so our vector field is going to be this thing here, and we're asked to use the divergence theorem. If you decide to do a flux integral because you're just a masochist, you're not using the divergence theorem. You got to use the divergence theorem here. So it asks you to get that flux integral. So the thing you'll have to do is to calculate the divergence of F. And so go through these entry by entry. X minus y, derivative with respect to x, is 1. And then x plus z, derivative with respect to y, is 0. And z minus y, derivative with respect to z, is 1. So we end up getting 2. Weird coincidence, we had 2 show up on just 2 of the things that I'd selected. But the nice thing is this is a constant. So we will have to do this volume integral across, I didn't really give the interior a name. I'm going to just write a W here because they use that in your book a lot, of 2 dV is equal to 2 times the volume. Well, the volume of a cone is given by 1/3 pi r squared times h. So we end up with 2 pi over 3. And that's it. If the divergence turns out to give you a constant, that's how easy these are. And that's kind of what we hope to have happen. So this one is not as nice, but it's still not terrible. Again, if you're a masochist, go right ahead and do the flux integral. So we've got the same surface as we did in the previous problem. So you could go ahead and use I said previous problem, the first problem we did. So you go ahead and use those parameterizations and everything. But I'm going to go ahead here and calculate out my divergence of this F. And so I come along here and say this junk here, I said, yeah, I pointed with the wrong thing. This junk here in the X entry, the derivative with respect to X is going to turn out to be 3 times 1/3 and then the X squared, right? Plus, now for the Y coordinate, I've got that Y cubed and then XZ's floating around. And so I'm going to end up with 3 times 1/3 y cubed, and then plus, and the derivative of this z minus x minus y with respect to z is just the 1. Because remember, you're doing this first derivative with respect to x, and so the yz's are just constants. You're doing the second derivative with respect to y, so the sine xy are just constants. Last one with respect to z, so the minus x minus y is just constants. So that means that we have x squared plus y squared plus 1. And conveniently enough, this looks like something cylindrical. That screams cylindrical coordinates for us, right? The previous example looked like a cone. That said either cylindrical coordinates or that you would do spherical coordinates if you had a rounded top on it. So, well, we're going to go ahead and do this with cylindrical coordinates, and I'm going to use the divergence theorem. So I'm going to say integral across the boundary of the f dot ds vector is equal to the triple integral across the volume there. And now I'm going to have to say x squared plus y squared plus 1 dv. Okay. And I am going to, on that, go ahead and put it into cylindrical coordinates, right? And then because it's cylindrical coordinates, I'll need to put an r, and then there's a dz, dr, d theta, right? So the z's, we had a flat top and a flat bottom, so it's just going to go 0 to 2. The r's, since we had, I guess you would kind of say it's flat, but flat in a cylindrical sort of way, it would go 0 to 1. And then thetas will go from 0 to 2 pi because we've got the whole cylinder on it. So doing the calculation there are no thetas, so we can just put a 2 pi up front. And there are no z's, so we can, well, actually, since there are no z's, we can actually just go ahead and do the same thing with that. It integrated 0 to 1, so I have a 1. And now we will integrate from 0 to 2. I get that all right again? Yeah, okay. Integral 0 to 2 of distributing that r in there, r cubed plus r dr. And so 2 pi times, and we've done these before, that when you're integrating, no, sorry. I was trying to take a shortcut, but it's not a shortcut we can actually take. 1/4 r to the 4th plus 1/2 r squared, 0 to 2. Plug that in, 2 pi times 1/4 of, let's see, 2 to the 4th is 16 plus 1/2 of 2 squared is 4. So 2 pi times 4 plus 2, 12 pi there at the end. All right. And that's it. So even when we've got one that's not just constants, the integration isn't super bad on these. Okay. So that's that. See y'all in class.